welcome to another technical seminar on behalf of Pipeline Industry Guild. My name is Jonathan Starling. I'm the Deputy Chair of the Outfalls Intakes and Landfalls technical panel. I'm also Principal Engineer and Technical Manager for Pipelife. Today, I have the pleasure of introducing Juan Jose de la Torre Suñé from Sener Group in Spain. He will be giving a presentation today on case studies and lessons learned from his recent work on intakes, circulations, and outfalls. Just before we start, a couple of the usual things, just to confirm that this meeting is being recorded and it will be on YouTube afterwards. So by taking part, you are consenting to that. As normal, if you can all keep your microphones muted and your videos off, then you won't be part of the recording. And any questions you have, if you can put them in the chat, we will go through it at the end once Juan Jose has finished his presentation. So I'll hand over to you, Juan Jose.
Yes, good morning. Thank you for the invitation. Thank you very much. And if you want, I share the screen, yes, and we start with the presentation.
You share your screen.
Well, we are going to see some particular two projects, yes, two particular cases, and also we will comment some learned lessons that we obtain in these projects. I'm working for 24 years in Sener company, yes, in hydraulic works department, and I've been involved in all types of hydraulic works, but in particular in intake and outlet systems for different kind of plants. This is our global footprint from Sener Group. We are all around the world. This is some data, general data. We are more than 300 people, and the turnover is varying depending on the year. Yes, about 1,000 million, 1 billion. Yes, these are our main departments or engineering groups. We, as hydraulic engineering team, we are primarily working for mobility. That means civil works and also for energy. Yes. In the case of mobility, we are working in railways, in highways, airports, ports, and also in the hydraulic engineering of all kinds, but as an engineering company. In the energy sector, we are working also as an EPC contractor. Yes, we have developed engineering of different industrial power plants, LNG plants, also renewables, either for a different contractor or a company, or for ourselves as EPC contractor. Yes. This is just an overview of our capabilities in intakes and outfalls. We will focus in two projects, yes. But just as an overview, we have developed more than 60 projects worldwide since 2004. And as you know, these kind of projects are very different. They vary a lot, sometimes with tunnels, sometimes with low flows, with high flows, with biological issues. And we wanted to share two cases, yes, one in Mexico and one in Argentina. We have worked in cases like in Holland, yes, we are still working in an enlargement of the plant, the LNG plant in Netherlands. Also in Termozulia in Venezuela, we made Termozulia 1 and 2 in Maracaibo Lake. And these were the intakes, Termozulia 2 and 3. But these works were never ended due to some lack of money and management in the country. This is the first EPC contract that we developed in Sagunto Port in Spain, LNG plant. This is a dissipation basin because there was a lot of wave height. So in each project there is a different issues. There are different issues. Well, this is just to let you know, because I know that in the panel there are many companies involved in offshore wind projects. As you know, in Spain, we don't have shallow water. So these projects became very late in comparison with the North Sea, for example. But in the last 4 years, we have developed many projects. I made the list here, yes, and developed engineering capabilities for optimization of the park, to develop the complete engineering, also onshore works, and in particular the shore crossings, which are also very common with other hydraulic works, as outfalls, for example, or pipeline crossings. So we are involved in shore crossings in general. I like to use some links to websites. We also developed the semi-submersible platform with less than 4,000 tons, which is very competitive. And one prototype will be built this year. So this is also part from our work. Yes. This is the third project we are going to see today. It's in fact, Martin Berry contacted me to explain this project, because he found that it was very atypical or very big. Yes. This is a project in the northwest side of Mexico, but not in the Pacific. It's in the Mar de Cortés. That's important because wave height is low. Yes, the average significant wave height is only 25 centimeters. And in fact, that's the reason that it was possible to make the project with steel pipes. Yes. We have an intake and outlet system for Empalme 1 and Empalme 2 combined cycle plants, and they are in total 1,600 megawatt. The total flow is around 36 cubic meters per second. And the client is CFE, it's a public company, and it's very important for you to understand why we did this project in steel and not, for example, in polyethylene or in CRP or other kind of more usual pipeline for outfalls nowadays. It's because the client had mandatory requirements from the bid stake to develop the project with steel and with flanges and pipe by pipe. Yes. So with as many other prescriptions in the project, we had to comply with 100% of the prescriptions. It's learned lessons from previous projects. Each project has its frame, and in this case, the frame is the total compliance of the requirement. We analyzed this at the beginning of the project. We saw that it was feasible to develop the complete engineering, and of course the supplies and construction in time. And it was really a fast-track project where the intake, in this case, was critical and had to be developed in a very fast scheme, yes, and coordinated scheme. We were EPC contractor with OHL Spanish company, OHL Industrial, at 50% each, and we developed the complete engineering in-house for the intake and outlet system. Yes. The intake system comes from the sea, 2 pipes of 3.4 meter inner diameter in steel. And the outlet system starts at the charging chamber, and there are 2 pipes also, 3.2 meters, the same size, also in steel. The typical length of the pipes is 39 meters, yes, and there were 39, and they were installed one by one, yes, pipe by pipe. More images, yes, this is the storage area of the pipes. There were floated with flanges and towed 10 kilometers, yes, from Guaymas Harbor to the site. This is the planned location, yes, and this was done more or less 1 pipe per day at the end, yes. As you can imagine, the beginning is always lower, but then the construction yield increases. Yes. You can see the size of the pipes. They had manholes. They had also some verticality assurance structures. And we had to deal with some prototype or some new design in a very tight time. We also had an intake in a very shallow sea with less than 6 meters draft. The water depth was very low for such a high flow, yes. In fact, we didn't find any example with such high flow with low draft working fine. But it is true that, for example, in Pacific Sea, there are similar intake towers with only 1 meter more draft, but of course with more, much higher phase. Yes. The intake was also tested using a physical model in a wave channel, avoiding the entrance of sand and also the vortex formation and entrance of air. Yes. Well, this is just to have a dimension of the pipe. It was very important that at the time of installing the pipes, having the possibility of having some relative rotation between the pipes. So we had to invent, well, in fact, in several days or a few weeks, some joints to locate between the pipes to be able to rotate, and they allowed 0.4 degrees of rotation angle, relative rotation between flanges. If we didn't include this element, we would have an issue because between two steel pipes, you cannot rotate, so you can deepen in the sand or lose cover, yes? And also you need to adjust in every pipe. We made a very good topographical control to know that every pipe was in the right location, yes? The flanges were special. They are not standard flanges. They were designed with 32 to 40 bolts, yes, bolt holes to accelerate the installation of the pipes. So the divers were able to develop a joint bolting in only 1 and 2 hours. We had an inner joint at this location. You will see a better photo. And then we had an outer joint that gave a double layer of protection to avoid sand entrainment. The reality is that the 125 pipes and all their joints had no structural problem, and the joints behave well. Yes. Well, sorry. This is in the dry test that we developed. The man you see in the photo is the site manager, Miller now. He had a very good control and direction of the work, and he wanted to test in the dry before going underwater. That was a good idea to improve the temporary supporting structures and other elements that we use afterwards in the underwater. Yes. This is a detail during installation. You can see the joint here, the main joint. This joint was designed checking that it had no sectional buckling problems. That means that the joint collapses because it had to assure that sand didn't enter. Yes. Also, electrical continuity between pipes was also an issue to foresee from early project stages, even when the cathodic protection system was not designed. And we had also like different ways to assure the electrical continuity from the beginning of the project. This is an overview of the onshore work of the project. As the flow is high, they require important structures. You can see here the outlet channel, yes, to the sea. This is the plant. This is Empalme 1 plant. And on the side, it's Empalme 2 plant. It was developed by another EPC contractor, but all the cooling water system was designed and constructed by Sener and OHL. This element is the seal pit. We first used this design in a project in Argentina. We developed physical testing, and we adapted in all the other projects that we have done. Yes. It has a wire to assure the back pressure in condensers. This is the fill pit of Empalme 2. And I would say, a curious thing of this project is that it has recirculation heat treatment to avoid biofouling. That means that both Empalme 1 and 2 have what we call mollusk pits. This is common in Mexico. I also saw it in California, in areas where there is a lot of mussel productivity or mollusk in general. The heat treatment of the complete system from the pumps to all the pipes and condensers is based on the double pass through the condenser with lower flow. It allows to make reach very high temperatures, and as you know, most mussels, even in these areas, are killed after some hours of temperatures above 35 and even much higher temperatures. Yes? Here, I share a drone video that you can, I will share also the PDF presentation, and you can click and see a drone video with many details of the plan in the late construction stages. This is the outlet channel, yes, it was above ground, the outlet chamber, and here started the outlet, the outfall pipes, and the intake pipes came to this intake channel, yes, and for example, the layout of the complete plan was not able to be modified. It was mandatory from the beginning. Yes. More photos. This is the pumping station. There are the pumps, the main cooling water pumps for Empalme 1 and cooling water pumps from Empalme 2 from the other contractor. Well, it was a big pumping station with 50 per 35 meters in layout and quite deep. As usually when you have long intake pipelines. We had 4.2 kilometers total length of the intake and outlet system, offshore pipelines. So the head losses are high and you need a deep pumping station. And you see the gantry crane also. This is, we never saw this, but we use, as a curiosity, we use geotubes at temporary groin. We had seen other applications. Local contractors, it's important to listen to them, indicated that they did the shore crossings with sandbags, but we envisaged that it could be a good thing to use geotubes. As you know, they are filled with sand. We had used them in other projects, but not for this application. They allow lower wave action in the shore crossing straits, about 100 meters, a little more, and it facilitates the stability of the open cut shore crossing. Well, learn lessons about this project. Some of them we already commented. I will jump to this is about the mandatory requirements, about that the steel pipes will not be a good option for high fetch oceans, for example. The importance of the planning and the coordination between areas. At month 1, we didn't have even the site surveys. We didn't have even a basic engineering, only the our bit engineering, but without additional surveys. So in month 13 of the project, we were already installing the first steel pipes underwater, and we finished in month 20, the last one, 125. So as you know, the fast track scheme, we need to design all the pipes and prepare all the documentation before we had the geotechnical survey, for example. So you need to take some considerations in design to accelerate. Yes, this is very common. Yes. Also, the innovative flexible joints that you saw, we had to design them very fast and take them into account for in the detailed drawings of the pipes. So this the well-oriented planning, as I indicate here, is very important. Yes, the focus the engineering in the most critical elements and release them with urgency, leaving the less critical elements for later. Yes, you cannot ask for all the engineering in month 10, for example. It's not the best way to attend one of these projects. Yes? Then another difficulty of the project was the very high productive area in terms of biofouling and macropooling growth. It was easy to realize about that just having a look at the existing structures. This is a block that fell underwater. Only during 6 months it was underwater. As you can see, it became full of marine growth. So in these cases, it's very important to have chlorination from early project stages and temporary chlorination before you have the commissioning of the electrochlorination plant in this case, because electrochlorination plant needs a lot of time to buy, to fabricate, to transport, and to commission. Yes. So this is a very important point in all projects, in fact, and especially you need to chlorine before you start with the flows. Yes, with even the auxiliary water flows or low flows, because flows imply the entrance of nutrients to the system, and it's the point where the marine growth can start. So it's very important to start the chlorination before you start the low flows in the system. Yes. Of course, during construction, you cannot chlorine because you are still installing the pipe. But the worst moment is the start of the flow. I already commented about the cathodic protection system. You cannot wait until cathodic protection is designed to know what are the elements that you need in the steel pipe. So we had to solve that at the early stages. And another important point is to foresee that the marine construction with the small marine equipment, because that allows to use local contractors, which is normally an important reduction of costs in comparison with international big marine contractors. Yes? For example, the intake structures, it's better to use a float and sink scheme instead of just lifting them with a very big crane. Yes. 200 tons, more or less. These are more length lessons of the onshore part. Well, maybe this is more standard, but very important lesson for this project. And also, for example, for another project we have developed the last months in Mexico for the same client. It's the importance of solving the hydraulic recirculation and the complete system. It's also true when there is no recirculation, including the water hammer and aligned with the operational rules of the system. Yes, and especially recirculation systems, when it is very long, it can be a challenge to solve the water hammer issues. Yes, so it's very important to don't wait until the end of the project to check the water hammer. You need to work in parallel the design and the water hammer. Yes, and of course all the pump operation range that can change due to several reasons. This is a photo of the pumping station during construction. Well, it's for example, the gantry crane had 35 meters of span. So it's a big structure. It was about 14, 15 meters deep. So we changed to another project. I thought it was curious also to comment today. In fact, there are two projects that we developed the detail engineering in Argentina. It's this TFM project. It's this one. It was a combined cycle plant of 800 megawatt. And several years afterwards, for the same client, we developed the detail engineering of a new plant of additional 800 megawatt. What is important here is that when you have made a design and everything is constructed and operating, it was a key point to make a visit, and get all the ask a lot, yes, the right questions, and get all the information about the operation of the system, what could be improved. Yes, the system was working well. In fact, we can be proud to say that all our designs this time of intake, but also all hydraulic work are operating correctly. but there are always some small things that can be improved. In this case, for example, we, according to the experience, we made an adaptation of the trash rack system with a more powerful system, also with a higher width, yes, a higher area, to ameliorate the trash rack capacity, also a higher lifting capacity, and to have even a better performance than the existing plan and avoid kind of manual operations in the plant. So this is in Parana River. The cooling water flow is 17 meters cubed per second for each plant. It's in Parana River, which is a very challenging location. Many intakes had issues in Parana River and all these rivers nearby in Argentina and South America, especially because the erosion capacity is very, very high. Yes? You cannot make, for example, an intake with 2 riprap groins because it will damage due to erosion. Yes, we have general erosion, transitory erosion during high floods, that the flood, design flood is more than 60,000 cubic meters per second. So the way of solving the intakes, you will see in our photos, was with very deep groins, yes, with piles. Second steel pile groins to solve the erosion issues, and also riverbank protection with flexible mattresses that allowed and had a very good performance. Level variation was more than 7 meters, so that also complicate the design and the construction. This is the first plan, the intake structure, and this is the second plan, CVO, that also during construction in this case. We had some difference of levels. The system would allow a future hydropower plant, but as it was not included, required by the client, it was not included in the initial design, despite there is some 15 meters of difference in height. But also was the structure was also necessary due to the connection of flooding stormwater flow. Yes. Then this is the intake pumping station. These are the groins, the deep steel second pile wall groins, and this is the overview of the intake. Yes. We had, in every project, we have particularities with biological particularities. Here we had what they call camalotes, yes, in Spanish. It is like guidelines of plants that can have pumas and monkeys and snakes on them and arrive to the intake. So it was, and they complicate a lot the intake operation. Yes, you will see that we develop a diverting structure at the entrance. Another complication is the suspended sand. So the intake groins allow for a precipitation of at least the higher, the 0.4, 0.3 millimeter fraction, which is the more abrasive. And the plant was working without abrasion issues. This is an overview of the finally built intake. We had, in fact, a double line of dry racks for a better performance, one thicker and the other one with lower opening. And this, you can see the groins, this is the diverting structure for the floating elements, even though many of them entered. As you can imagine, in every project, we need to implement inventions, and with lack of time normally. Yes. So this is also during construction, the pumping station were diaphragm walls, reinforced concrete diaphragm walls with several levels of anchoring. It was the wagon drill developing the anchoring, and it's very important also as a learned lesson to separate the intake from the river. Yes, if you try to develop this structure very close to the river, you will have geotechnical issues or erosion stability issues in the connection. Yes, it's better to separate enough the intake, and at the end, this wall, the frontal wall, was demolished. Yes. Well, this is the last overview of the intake. And just as a comment, sometimes we need to think that intakes are very, very important from the operational point of view, very critical for all kinds of plants. That is valid for all of them. In fact, there are plant owners that have intake operative issues in all their intakes, in 100% of the intakes, yes, for several reasons. Yes. So it's a part of the project that is not as standardizable at its whole, because due to adaptation to the site conditions, but we need to know that the criticity of the intake system, especially these sea intakes and also big river intakes, we need to dedicate duly engineering and coordination, also to avoid impacting planning, but especially thinking about the final operativity, duplicating elements, whatever is necessary. Yeah? And these are examples of intake structures that were started to be built and were never used. Yes, this is one, and this is another one also in the same location, in the same river. Yeah. Here you have like more than 400 meters of diaphragm walls, and the structure was finally abandoned. Yeah. That's why just to give some importance to this kind of work. So thank you very much for the invitation again, yes, and forgive me for my English. And well, this is just some photos of the team that was involved in some of these projects, but in many more. Yes, at the end, is the important is our team. Yes, working on this, and for a lot of time, some of them for more than 20 years. Yeah? So thank you.